Okay, very good. I want to start by thanking the organizers and Jorge in particular for giving me the opportunity to talk a little bit about my work and to come to this very stimulating conference in this beautiful city. I'm very happy to have had an opportunity to get to know some people here as well as the area. So the topic I'm going to talk about is topological crystalline insulators and some interesting physics that we think can happen when you dope this material with magnetic impurities. My collaborators on this are Sahinur Reja, and that's this person and not this person, so please don't get confused. He's a postdoc with me at Indiana, my longtime collaborator Louise Bray in Madrid, and my colleague at Indiana, Chu Chang Jiang. Okay, so for this conference, I really think the right place to start this story is with the integer quantum Hall effect. So the two-dimensional electron gas with a perpendicular magnetic field, and around 1980 it was discovered that you get these very sharply quantized values of the sigma xy, the Hall conductivity at low temperatures. And David Thewlis came up with a rather brilliant idea for how to understand this by embedding this two-dimensional electron gas in the magnetic field, but also in a spatially periodic potential. And that's a well-known problem that was spearheaded by Douglas Hofstadter. He showed that you get what's now known as the Hofstadter butterfly. It's a rather intricate spectrum of bands and gaps that change in kind of a fractal way as you change the flux through each unit cell. For our purposes, it's enough to know that when you have a rational fraction of flux to magnetic flux quanta through a cell, you get a integer number of bands. And what Thewlis and coworkers, what became known as the TKKN group, recognizes that if you calculate the sigma xy using the Kubo formula for each of these bands, it's actually proportional to a topological invariant, in fact, the first Chern number. And so one then recognizes that this could give the robustness one finds to these quantized values of the sigma xy, because you can inherit the robustness of a topological number. And moreover, as we've been hearing, when you form a system that has boundaries rather than being in a periodic, having periodic boundary conditions, you get conducting edge states even where the bulk is insulating, and the number of conducting edge states is closely tied to the Chern number of the bands. Okay. So for a long time, people thought, or for a number of years, people thought this was something very special to the quantum Hall system. But then a few years later, Duncan Haldane showed us that, in fact, you can create another model that has similar behavior. And we saw this picture a couple of times yesterday. So in this Haldane model, we basically have a honeycomb lattice with some pattern of flux through the system, and both nearest neighbor and next nearest neighbor hopping. And this pattern of magnetic flux is such that when you average it over the unit cell, you actually get zero. So there's no net flux. But nevertheless, the time reversal symmetry is broken in this system. Because it has broken time reversal symmetry, you can get a non-zero sigma xy. And what he showed was that for certain combinations of the parameters of this type-binding Hamiltonian, you in fact get a quantized sigma xy, which is once again related to the Chern number of basically the band structure. Okay, so we started to get a hint that one can go beyond the quantum Hall effect and have topology relevant to the physical properties of the system. But again, it sort of appeared that somehow breaking time reversal symmetry was necessary. And then right around the time that graphene became available as a material, that was really in 2004, well, Charlie Kane decided to sort of throw his hat in the ring in studying this material, and had a very interesting idea to look at what happens when you include spin-orbit coupling in the graphene system. And in particular, he found that the symmetries allowed for a spin-orbit coupling that gives you essentially the same Hamiltonian as Haldane found, except there's sort of two copies of this, one for each spin. And if you write down the continuum version of this type-binding model, so this is the usual Dirac Hamiltonian that you get near the K and K prime point for graphene, the spin-orbit coupling gives you another contribution which has the third Pauli matrix, and so will gap out the spectrum at the Dirac points. And what's very important is that the coefficient of this changes sign if you flip the spin. It also changes sign. I didn't show it, but it also changes sign when you go from the K to the K prime value. And you need these behaviors to respect the symmetry. So this is essentially two copies of the Haldane model, kind of in opposite directions, if you like, for the two different spins. So there's no charge quantum Hall effect in the system, but because it's kind of like you have quantum Hall effect for each spin, you get a quantized spin Hall effect. And so this was the beginning of a lot of what we're talking about in this meeting. And it's very important that I should point out that Chu Chang Jiang and his coworkers found almost really the same physics, but in rather different materials right around the same time. Okay. So what I like about this particular model is it gives us kind of a very pedestrian way of understanding the topology that's relevant here. And that's by noticing that the Hamiltonian, which is just a 2x2 Hamiltonian, it acts on the space of sublattice wave functions, the amplitudes for the two sublattices in the wave functions. We can notice that this 2x2 Hamiltonian is kind of like a Zeeman Hamiltonian with a magnetic field that has an amplitude, but also a direction, an n hat, that changes as you change wave vectors. So it's like a Zeeman field in K-space. And so we could look at one of the bands. For example, if we looked at the upper band, we'll find that the solution to this, the eigenvectors of this, point along the n hat direction. For small k, that means the spinner would point towards the north pole. But as we increase k, these off diagonals become increasingly important, bringing the spinner down to the equator. And then the way this kx plus iky is put in here, as we basically rotate in the kx ky plane, we're going to make that spinner go around the equator. And so the important point about this is that this Hamiltonian defines a mapping to the Bloch sphere that covers exactly once the top of the Bloch sphere, the upper half of the Bloch sphere. Now that's literally only half the story because I've only looked at what's going on near the K point. But if we go elsewhere in the Brillouin zone near the K prime point, well, as I told you, I have to flip the sign of the spin-orbit coupling. And so that means we end up covering near the other point, the other half of the Bloch sphere. And so we've managed to cover the Bloch sphere once in every point on the Bloch sphere once and exactly once. And that coverage is one way of understanding the meaning of the Chern number in this particular context. Okay, so moving on, it was quickly realized by both Charlie Kane and people working with him and the Chu Chang Jiang group and people working with him that there are three-dimensional versions of this. So one of the earliest ones to be studied was bismuth and timonide materials. And if we look at the Brillouin zone now in 3 dimensions, we have a shape something like this. And you can consider a surface, for example, perpendicular, or the 1-1-1 surface, perpendicular to basically I think it's the gamma t direction in this case. And so that defines a surface Brillouin zone with a center at what's called the gamma bar point. And this point here is what you could call a time reversal invariant point. If we have the time reversal operator act on the Hamiltonian, this point will come back to itself. And what these people recognize is that because of Kramer's theorem, we actually have to have 2 different states at the same energy at exactly this point in the surface Brillouin zone. They must be degenerate because of the time reversal symmetry. And if you move away from this point, those 2 states can now get admixed, and you'll generate a Dirac cone so that we end up with states at the surface which are gapless. And so that's very interesting because the band structure has a gap in its spectrum. So of course in the bulk we have an insulator, whereas on the surface we have conducting states. And the beautiful thing about this, and we heard a lot about this in the last talk, is that there's protection. This gapless nature of the surface state is protected in this case by time reversal symmetry. Okay, so I actually want to talk about a way of sort of developing these surface states rather explicitly. And this story actually again began with Chu Chang Jiang and his co-workers. They started by considering a slightly different topological system, bismuth selenide. This is a layered material. It's rather anisotropic. Here is its Brillouin zone. And they were considering a surface here, the 1-1-1 surface, again, perpendicular to this direction. And again, there's a time reversal invariant point there at the gamma bar point. And there are four, if you look at the states in the Fermi energy, there are four orbitals that are relevant. There are sort of two different parity states and then two different spin states. So there's four states that are relevant, and they expanded their tight binding model near this gamma point, and for the three-dimensional system came up with this sort of relatively simple 4x4 matrix Hamiltonian, and it's developed up to quadratic order in the wave vectors. So what you see is, I think the most interesting part is to look at the diagonal. These M's here are kind of a mass matrix. And what you notice is that as we change our value of K, as you move out from K equals 0, which is at the gamma point, you have one sign of the mass. But if you move far enough away from that point, the mass changes sign. Okay, so that changing of sign of mass, that's sort of like the Z component I'll show you this in a moment. It's kind of like a Z component of a magnetic field, and it's changing direction. And it turns out that in order to get the topological nature of the band structure, you need to have this M0 have the same sign as the B2 and the B1 over here. So let me show you that a little more explicitly, and this is the way they look at it in their paper. If we set one of these wave vectors to 0, for example, the KZ direction, which will be perpendicular to the surface we're ultimately going to look at, we end up with a two-dimensional Hamiltonian of this form. And what you notice is that there are three matrices coming in here. There are 4x4 matrices, but they're made up of a matrix that, a set of matrices, Pauli matrices that act on the parity states, and a set of, this is actually the identity, the sigma x and sigma y act on the spin degrees of freedom. But what's important is that these are 4x4 matrices coming in. There are three of them, and they mutually anti-commute. So we can think of them as being algebraically the same as a sigma x, sigma y, sigma z, if we like. And so once again, this can be used to define a direction on the block sphere. We can think of a generalized kind of spinner. And because this has us pointing from up to down as the K gets larger, and this causes us to wrap around in the azimuthal direction, once again, you're going to cover the block sphere once and only once, right? So again, we get the topological, kind of the non-trivial topology in this band structure, even at this level of just writing it down to quadratic order. Did I have something wrong? OK, it's possible. OK. There could be a typo. Yeah. They're the usual Pauli matrices. They're just acting on a different space than the sigma matrices. They're acting on the parity space. There are two parity states. The sigmas are acting on the two spin states, but they're still Pauli matrices. Again, it's the usual thing. It's 0, 1, 1, 0 for tau x, etc. It's the same thing. I'm just writing them with a different notation to emphasize that they act on different spaces, but they have the same explicit forms. Okay. All right. So given this this expression over here, so you can actually figure out explicitly the surface states. In this case, we're going to be interested in the surface states perpendicular to the z direction. And again, Chu Chang Jiang first argued about this, or really kind of showed that this can be done. But there are various versions of this, and of course, I'm going to talk about my own version because that's the one I did with Louise. That's the one I kind of understand best. But it's very similar to what came up in these earlier papers. So the way you proceed on this is we're going to go to the surface time reversal invariant point. So we set the kx and ky to 0. And I want to look for states that are evanescent in the bulk. So I'm going to put the appropriate operator in place of the kz over here. And so we want states that vanish at the bulk, but we also need some boundary condition on the surface. And we're going to impose a very simple boundary condition, which you're going to see we can actually implement, that the wave functions vanish when you're exactly on the surface itself. Okay? So there's several steps to this kind of algorithm to doing this. The first is that we need to look at evanescent states, and so we have to solve an eigenvalue equation There's an inverse evanescence length, which is this lambda. You get this equation from solving this. You see it's quartic, so it always works out that you can find two values of lambda, which are almost always different, two values of lambda, which give you evanescence when you go into the bulk. The next step is we're going to take for a given energy these two values of lambda and ask if we can find, when we find their eigenvectors, if we can find a situation where those eigenvectors are the same for both values of lambda. And that gives you another condition that you have to be able to solve. And it turns out you can solve these two equations and get non-trivial results, solve them simultaneously, provided that you have this requirement on the coefficients, which it just so happens are exactly the requirement you need to meet for the band structure to be topological. Okay, so that works out nicely. So if you solve both these equations, which you can do quite explicitly, we'll find the u's here, we'll find the actual eigenvectors, and because of the time reversal symmetry, you're going to find not just one but two solutions to this, which are actually orthogonal to one another. And so I can form these kinds of combinations, which you see vanish at z equals 0, which is right on the surface, and are evanescent in the bulk. That's just what we need. We have states that are now confined to the surface. So the final step in this is then to go back to your bulk Hamiltonian and project it into the space of surface states. And the result of this gives you a Hamiltonian that's linear order in the Ks and has this Dirac nature to it that we expect. If you actually compute the spectrum, that's these, I guess, these purple dotted lines over here from this Hamiltonian over here. You can compare this to the results from just simply taking a slab of the materials or the tight binding model that underlies all this and numerically diagonalizing it. And that's basically what's in the rest of the figure, these yellow areas, as well as the solid lines over here. And you see basically the match between the tight binding model and this simple-minded way of constructing surface states. They really match quite well. All right. So that lets me come then to the main topic of the talk, which is these topological crystalline insulators. And here what's different from the topological insulators that we've been talking about is that it's not time reversal symmetry that gives you the protection, but some crystalline symmetry. And really it was Liang Fu who kind of started this whole field and showed that there's a variety of types of crystal symmetry where you can get this kind of behavior. Now the material that's kind of the paradigm for this this sort of topology is this tin telluride and alloys of it with lead. The symmetry that's relevant, the crystalline symmetry that's relevant here is a mirror symmetry. The system is a rock salt system. These purple ions are supposed to be the places where you can have tin or lead, and how much you have of each depends on how you've alloyed the system. And you can see that this rock salt system has a lot of mirror planes in it, so there's a lot of opportunities to get this kind of crystalline protection. Now, the orbitals that are important in forming the band structure of this, it's a little more complicated than when I showed you previously, because we need all three, px, py, and pz orbitals, and there's a sublattice degree of freedom as well as a spin degree of freedom. So actually, when you start this, you're starting by looking at 12 by 12 Hamiltonians, which is a little bit intimidating. But you can begin to simplify this, as I'll show. So the first thing is to put together these three spatial orbitals into a triplet with a vector creation operator that gives you the px, py, and pz. So this creates three entries in a vector state. And then there's kind of a standard model for this material. It's written out rather explicitly in one of the early papers that Liang Fu wrote, although in fairness, he didn't really invent this. It was their earlier papers that use exactly the same model, although it's not written out as clearly as he did. So here's that model. It looks a little intimidating when you look at it first, but if we take it one term at a time, it's not that bad. The first term is just an on-site energy, which gives us different values for the on-site energy for the purples and the greens. And what's nice about these materials is the effective value of the on-site energy in the purples depends on the alloying. You can use a virtual crystal approximation basically to continuously change the on-site energy over here. So the energies of the orbitals on the two sides can be changed depending on how you alloy the material. So it gives us a handle in the lab on looking at a variety of basically masses here. The next term is a nearest neighbor hopping term. You notice this D vector here. This is just something that points from one unit cell to the next unit cell, or from the one at R to the one at R prime. And you'll notice that the hopping is directional. So for example, if I look at the px orbitals, those will only come into hopping between neighboring sites that are separated in the x direction, and similarly for the y and z directions. Then there's a next nearest neighbor hopping, which is also directional. And finally, an on-site spin-orbit coupling. So if you look at these term by term, each of them is rather easy to understand. Okay, so this is has an underlying FCC Bravais lattice. So this is its Brillouin zone. The interesting points, it turns out, are what are called the L points, which are at the centers of these hexagons. And there's a lot of nice things that happen at these L points. For example, when you set the k value equal to what it should be at one of the L points, you find that the nearest neighbor hopping Hamiltonian actually vanishes, which means the Hamiltonian breaks up into two separate blocks, two 6x6 blocks with well-defined sublattice index. Yes?
Hopping is directional, does it break hermiticity?
No, it doesn't break hermiticity. No, no, the Hermitian conjugate is always there. Mm-hmm.
Oh, Hermitian conjugate.
Mm-hmm. Yeah, the Hermitian conjugate is always there. Mm-hmm. Okay, so we begin to simplify things, right? We're down to 6x6. And then, as I said, there are a lot of nice symmetries. For example, if you look at the gamma L direction, it's easy to convince yourself that around the L point, there's a threefold symmetry axis. It's, again, a bunch of mirror planes, one of which is going to become relevant in a moment. But if we look at the threefold rotational symmetry, we can then break up the eigenstates into three blocks of different values under the threefold rotation. And so then I get 6 divided by 3. I get a bunch of 2 by 2 matrices, and you can diagonalize this by hand and get the eigenstates explicitly. So if we look at the states that are near the Fermi energy, there are 4 of them, and I've actually written them out almost explicitly over here. They're written in terms of states with well-defined eigenvalue under the C3 rotation, as well as well-defined sublattice indices. Remember, at the L point, sublattice is a good quantum number. The U's and V's are coefficients in terms of the type binding parameters, which again can be written down explicitly. They're rather messy. There's no reason for us to look at them in detail, so I haven't shown it to you, but we do know what they are. Okay, so I end up then with 4 states that are relevant at the energy scales we're interested in, basically near the gaps in the band structure. It's 4 states, so for a particular L point, and we're going to have to look at 4 L points. There are 4 distinguishable L points here. But let's look at just one of them for the moment. So this particular L point in the 1, 1, 1 direction. Okay. And we can then expand the Hamiltonian for small wave vectors around that point. And we're going to go, because I want to use this method I described to you, up to quadratic order. All right, so now there's wave vectors here defined in a particular coordinate system. So this is starting to buzz. So, okay, so the Q3 here is a wave vector pointing, it's this, okay. I see. Okay, wave vector pointing out of, basically in the 1, 1, 1 direction. And then the Q1 and Q2 are perpendicular to this. This is what you get from this expansion. And I should say that you can actually write down the linear terms, the things that are linear in wave vector, completely just based on symmetry. You don't have to do all this hard work. And that is what Liang Fu actually did initially, and he was able to come to a lot of conclusions just knowing about the symmetries of the crystal. But we wanted to do things more explicitly. We needed this quadratic terms, so we had to go and work a bit harder. All right, so we can go kind of through, and I need to say what these matrices are. The taus are now acting on the sublattice degree of freedom. And then we have a sigma, right? Yeah, we have sigma tilde matrices, and these are acting on I have 2 states that I showed you on the last slide, which are states of with rotational eigenvalues, and these sigmas are acting on that space of the different rotational eigenvalues. Okay. All right, so we can set this Q3 to 0, and then just write this down as a function of Q1 and Q2, and we get something very similar to what I showed you a moment ago, where we get 3 matrices that are mutually anti-commuting. Again, we can then see that if we take this as a mapping from the Brillouin zone to the Bloch sphere, we'll end up covering the Bloch sphere exactly once. We enclose the origin. Once again, we have the interesting topology, provided we have a particular sign signature obeyed. All right. So we can go through the same kind of states and get our Dirac points and the explicit surface states. We find that there are two such states, and you can write them down different ways. One way to do this is in terms of different sigma 1 tilde eigenvalues, and they're going to be degenerate, and they're degenerate because there's a crystalline symmetry. And the protection here is actually that the sigma 1 tilde actually carries out a mirror reflection across the x equals y plane. That guarantees that you're going to have two states that are degenerate at basically the projection of this gamma L direction onto the surface. That's called the gamma bar point. Okay, so again, we go through the kind of exercise I showed you previously, projecting this now, our Hamiltonian, onto the surface states, and lo and behold, you get a surface Hamiltonian that is in the wave vectors perpendicular to the direction, well, along the surface. And you also can figure out the energy from this method. You can figure out the energy of the Dirac point of the surface state. Now, this is not everything you get on the surface for this 1, 1, 1 direction. There are other relevant points, which are the projections of the three other L points onto the surface. And those end up at the sort of middles of the faces of the surface Brillouin zone. Those are known as the M bar points. But you can go through this exercise, and we did. You get something not exactly this, but something that's got some anisotropy in that case. But nevertheless, it's basically the same idea, but the energy of the Dirac points, there's no reason for them to be the same as they are at the gamma bar point. So we end up with 4 Dirac points on the surface, but at 2 different energies. Okay, and this, again, really just based on symmetries, this is something Liang Fu, this is not something new. This is something Liang Fu showed us a while ago. What's different here is that we actually know what these surface states are explicitly. Okay, and so there are the places where we have the different energies. As it works out, the E gamma bar is a little bit higher in energy than the EM bars. Right? So you can see this in a couple of ways. This was actually shown in ARPES experiments from Story's group, and that's showing the 2 different types of Dirac points on the 1, 1, 1 surface with slightly different energies. And one of the M bar point has anisotropic Dirac cones, whereas the one at the gamma bar is isotropic. You again can see the same kind of thing in type binding calculations. These are our own type binding calculations. If you look carefully, you can convince yourself that these 2 Dirac points are not at the same energy. Okay. So finally, I'm ready to come to what we wanted to do with this. We put magnetic impurities into this system. And this is something that people have been doing for a very long time. This is one of the early, the tin lead telluride system is actually one of the earliest examples of a dilute magnetic semiconductor. So for other reasons than topology, people have been looking at this actually since, well, a very long time, I think the 80s or even possibly earlier. And this is just one example of something you can find in the literature. This is again from Story's group, showing that at low temperature, I think this is only 3% doping of manganese into the system, you get a hysteresis curve showing the ferromagnetism in the system. And the underlying mechanism for this is very well known. We put in these magnetic impurities, and when people treat this theoretically, it's common to use what's called the SD Hamiltonian, which I'll show you in the next slide, for the coupling between the magnetic impurities and the conduction electrons, or holes in this case, that you've introduced through the impurities. The magnetic moments then interact by what's called the RKKY interaction, which is basically an interaction between magnetic impurities mediated by the conduction electrons. Okay? One thing that's going to be very important and useful for what I want to say is that when you put in these magnetic impurities, they always substitute for these purple sites. They only go into one of the 2 types of sublattices. So we asked the question, what happens if we actually remove these electrons in the bulk, for example, by compensation doping, right? We can leave the impurities with the magnetic moments, but we can get rid of the conduction electrons. We can again bring the Fermi energy back to the gap, and then we'll still have surface states if we're in the TCI limit. And so we'd expect the impurity magnetic moments near the surface to interact with one another through the surface states. And we wanted to see what kind of magnetic properties that gives you. Okay, yeah? The whole thing is doped. The whole thing is doped, but, okay, but we have to make a model of this. When we go into the insulating state, there are really no carriers in the bulk. So those impurities, which are relatively dilute, don't communicate with each other, and there's no reason to think they would order. So we're actually going to ignore the ones in the bulk, ultimately. Right? But the ones near the surface do communicate because of the surface state, so those are the ones we're going to model. Okay. All right, but it's not impurities dropped on the surface. That's an important point. All right. Good. So it's actually not too hard to convince yourself that you could get ordering of the surface magnetic moments because if we have such a surface state with a Dirac point, well, you can set up, let's say, a ferromagnetic state that breaks the mirror symmetry. If you break the mirror symmetry, and for example, your Fermi energy is right here, if I dope things just right to put the Fermi energy at the Dirac point, when I order the magnetic moments, I'm going to break the symmetry and open a gap and push the electronic states down so I can lower the energy, the total electronic energy of the system. So this gives you a reason to think that magnetic ordering can occur. And this is basically the physics that we looked into. Okay, so here's that SD Hamiltonian. We're going to also project this into the space of surface states. And here I've written them out a little more explicitly than previously. The entries here are in terms of eigenvalues of the sigma 3 tilde operator, which is basically the rotation operator around the different gamma L directions. And one thing that's very nice about this is that these states have equal weight on the two sublattices for both the gamma bar point and the m bar point, although there's a complicated phase that comes in the m bar point. But actually, because we have all our atoms on the same sublattice, we really don't even need to deal with this complicated phase. All we need to know is that the weights are equal for the two sublattices. So projecting this Hamiltonian then into the surface states is rather straightforward. Is rather straightforward, and we can then figure out the surface Hamiltonians in the presence of magnetization on the surface. So we're going to start by assuming that these magnetic moments have actually polarized. They're going to assume they're ferromagnetic and then come back and check if that assumption makes sense. And moreover, I'm going to treat this in a mean field theory so that the impurities on the surface or near the surface will give me just an overall kind of a Zeeman field near the surface. So with this change in the Hamiltonian, we can then write this down rather easily. And so what you find is that you get terms in the Hamiltonian that indeed open a gap, and the magnitude of those gaps are proportional to the magnetic moment in the direction, in the gamma L direction, right? And remember, there are 4 L points, so there are 4 different gamma L directions here, right? So for each of these Dirac points, we open a gap, but the size of that gap depends on exactly which direction the magnetization is pointing in, and there's a competition among the different Dirac points. Okay. Okay, and indeed, which of these gamma points, or rather, which of these surface Dirac points wins out will depend on the chemical potential, just how doped you are in the surface states. Okay, so now we're going to turn to some numerics. So we model our system as a slab. It's actually a layered system when you're in the 1-1-1 direction, or with your slab, it's perpendicular to the 1-1-1 direction. And it's the computations that Sahinor did had 48, basically sort of 48 layers in this slab. And we put some atoms, magnetic moments, near the surface. And we actually place them in such a way to make the coupling to the states in the gamma, associated with the gamma bar surface states, and associated with the m bar surface states equal, so that that's what we expect to happen on average in the real system, where the placement of the atoms is going to be somewhat random. Okay, so if we put our magnetization along what I call along the gamma bar direction, which is really along this 1-1-1 direction, you see that the gamma bar gap opens up the most, whereas if we put it along one of the m bar directions, the gamma L direction associated with one of the m bar points, that will get the largest gap. Okay, so we can push down these various states in different ways. All right. Okay, so this is the main result then. This is showing the energy as a function of orientation for these magnetic moments. So this is a relatively dense case. Of course, you can't make it too dilute because the unit cells get too big to handle numerically. But this is sort of the simplest calculation. And we've done energies for fixed N and also energies for fixed chemical, total electronic energies for, or free energies, I should say, for fixed chemical potential. And they show 2 types of results. when the chemical potential is near this E gamma bar point, so near the Dirac point of the gamma bar point, you basically get a twofold symmetric low energy direction. It's basically along the gamma L direction, either parallel or anti-parallel. This is showing only the top half of the Bloch sphere. There's a bottom half that's symmetric that I have no good way of showing you. Right? Whereas if the energy is near the energy of the M bar points, you get actually 6 minima. I'm showing again 3 because I'm only showing the top half of the Bloch sphere. So we have twofold symmetry for our magnetization in this case, whereas we have in these kinds of cases 6-fold symmetry. In this calculation, we tried checking things in a more dilute limit. Only 2/9 of the sites actually have 5 minutes. Only 2/9 of the sites are actually occupied, and we're able to show that depending on your chemical potential, you're going to have one or the other kind of orientation, the lowest energy. Okay, so the interesting thing about this is we can change the orientation of the lowest energy state just using a gate. All right, by using a gate, you can change the density of electrons at the surface. All right, so I want to say a few things about spin stiffness, but I'm running out of time. We checked when we reorient these magnetic moments that we indeed will raise the energy. So being magnetized, being ferromagnetic, at least linearly, seems to be the lowest state. So let me go on here. All right, let me simply go on here, and I'm going to skip our comparison with graphene and come to the main point. There we go. All right, so there's some interesting consequences then for what kind of disordering you can get as a function of temperature in these systems, all right? Because this is actually a relatively rich system. As I change the chemical potential, I have different possible orderings. So for example, if we start with the chemical potential above both Dirac points, in that case, we have the twofold symmetry, the lowest energy state. And you can convince yourself that if this is well above, both Dirac points, that if you look at domain walls of this Ising ordered kind of system, they should be finite in energy. And so we believe in the situation that as you raise the temperature, there should be basically a thermal disordering in the Ising class. Now, something funny happens if you put your chemical potential right through one of the Dirac points. What I didn't show you in this calculation of spin stiffnesses is that you actually get something that has a long-range nature when you're right at the Dirac point. And so a model of this would give us kind of an energy functional. I'm writing it as E2, giving us sort of the two low energy directions, but then a spin-spin interaction, which it turns out, for things to be consistent, should fall off as 1 over r cubed. This is an example of what in the literature you can find called the long-range Ising model. There's some literature on this, and one of the things we found for this particular exponent is this should have a disordering transition, but instead of being in the Ising class, it ends up having mean field exponents. If we continue to change the chemical potential, this is now going to give us the lowest energy configuration. So now it becomes kind of a 6-state clock model of some sort. And again, if we go through one of the Dirac points, we're going to have something that's long range. Sorry, that shouldn't be Ising model, but it's something that's long range, and we don't really know what kind of transition. I didn't find anything in the literature about this particular 6-state with a long-range interaction. Maybe it's mean field, but this is something we want to figure out, actually, what kind of transition you get for a model like this. And finally, when you go all the way below, so that you're not through either Dirac point, we have, again, broken 6-fold symmetry, and now domain walls between different orientations are going to have finite energy per unit length. And years ago, when Jorge Jose wrote this paper, beautiful paper that he told us about, one of the representations you go through in these various duality transformations involve a realization in terms of domain walls. And so you can convince yourself from these results that this actually will give us thermal disordering in the Thewlis class. So we kind of come back to this other type of topology that was relevant for the Nobel Prize. So I don't know if I've gone over my time. Probably I have. Let me just put up my summary. That we've just submitted this article, so you can find it on arXiv. It's over there. And let me thank you for your attention. Okay.
So in your model, you just ignore the ferromagnetic order in the bulk because there's no carrier.
Right, so there isn't any ferromagnetic order.
But we know there are ferromagnetic insulators. So can you justify how to ignore it?
Well, I mean, experimentally, it's not seen, right? When you get rid of the carriers in the bulk, you don't see the ferromagnetic order.
There are examples.
There are examples, but not for this material.
Not this one. Right.
Not this material.
Okay.
Right.
Yeah.
Any other questions? Maybe you can talk about your checking of the ferromagnetism.
Sure, thank you. I skipped over it, and it's an interesting subject. I needed another 5 minutes or 7 minutes for that. Yeah, so, but that's an important point because we made the assumption that it's ferromagnetic. Right, so one thing we did, we took this geometry, so a numerical thing we did, which lets us check the ferromagnetism kind of at short distances, is to take this model where we have 2/9 of the sites occupied and basically turn the spins in different directions. And then we found sort of a difference of energies that lets us actually look at, well, basically whether the energy is raised by twisting these in opposite directions. And indeed, we find the energy always goes up as you twist these away from one another. So that tells us when impurities are close together, they'd prefer to be aligned. The other thing we can do is analytic. We can look at this, what happens if I put in a twist that varies over long distances in the magnetization, right, with some wave vector q, and then ask ourselves, how does the energy vary as a function of q? And you can do this in second-order perturbation theory. So that's how we did that. And so the answer actually depends on whether the chemical potential goes through the Dirac point when there's no magnetization or whether it gives you a Fermi surface. So one thing we found is that when there's a Fermi surface present, in fact, the result is independent of Q. And that worried me at first, but then I remembered, or I was reminded by Louise of earlier work we had done on graphene, which is actually a very similar calculation, where we still have a single Dirac cone in that case that we were looking at. And basically, you compute the magnetic susceptibility, and it's a very similar calculation to the second-order perturbation theory calculation. There are two contributions, one when you're at zero doping, and this ends up giving you something that's linear. Actually, I'm showing you with the slope in the opposite direction. This is minus chi0 for reasons you'll see in a moment. And actually, what it does is it starts at a constant that's cutoff dependent and then comes down. So that's this susceptibility at zero doping. Then if you introduce the chemical potential, you find that you get something of this shape with the well-known cone anomaly at 2kF. And I've showed things this way so that you'll clearly see that this slope and this slope are exactly the same. So that's very important. When I add these two contributions together, these two things will cancel out, so you end up with something that's completely flat at small q. And that's why previously I found, that's why we found that when the system is doped, we get something independent of q. That's actually what comes out of the calculation. Okay. When we're in the gap, when we put in this uniform magnetization and now try to put in the twist, we do get a spin stiffness that's non-zero. And it's a little bit of hard work, but you can figure out these coefficients here, and this is the result. You can get them quite explicitly. And you can check that these coefficients are such that if you put in a twist, you always raise the energy again. So again, it's ferromagnetic. The one thing that, again, gave me some pause is this is the gap in the absence of the perturbation. And these stiffnesses seem to be diverging. And that actually turns out to be right because when we get rid of the gap, we're again back to the graphene situation where we had this linear dispersion. And basically, so we have something linear in Q instead of quadratic in Q. And this is sort of the closest the calculation can come to telling us that it's giving us these, that's giving us these coefficients that diverge when the gap vanishes. And that's why you end up with these sort of long-range couplings that I was talking about in the following slides. So that was that part of the story. Yeah. Can you
please go back to the numerical calculations of ferromagnetism?
Do you mean the stiffness?
Yeah.
Yes?
Yeah. So here you have simply the double exchange model.
Sorry, these are I'm not sure you mean like that. You mean the SD Hamiltonian? Is that
Yeah.
what you mean? Yes, that's right.
So there is no, so your Hamiltonian, when you do this minimization, is simply the kinetic energy of the electrons and this S dot S.
Yes, that's what's in it.
Okay.
Yeah, that's what's in it. It's sort of a simple-minded type binding Hamiltonian.
So this is strictly speaking two-dimensional ferromagnet?
Yes, correct. Right. That's right. But it's showing you the zero temperature and then making some speculations about what happens when we put in finite temperature.
Any other questions, especially from the people, the backbenchers? No questions? Yes, good. Thank you. No, that's one question.
Oh, there was a question. I'm sorry.
No, sorry, I'm flattered. This one question which I'm interested in, if this model can also apply to other materials such as MS2. Or
Well, that's a two-dimensional material, right?
Oh,
so, right, I mean, you can apply that's a little like looking at graphene with magnetic impurities, which
Yeah.
people have done. They've done it actually with MOS2 as
But
well.
I just saw the first few slides in your talk because it actually has a honeycomb lattice. Then you have a Hamiltonian, and and the 4x4, which is kind of analogous to the bilayer MS2.
Oh, yes,
Hamiltonian.
that's true. Yeah, you could get that in a bilayer system. You'd have a 4x4 Hamiltonian, right? The simplest Hamiltonians for the single layer are the 2x2 models. But so I'm not sure what question you're asking.
I'm just curious if MS2 can be just play something and add some topological thing.
Yeah, for the single layers, and I'm not sure about what people have done in the bilayers. Certainly, the single layers, people have looked at RKKY interactions among impurities, and there's some similarities to things that I've talked about here. Yeah, a lot of that's quite numerical, actually.
Thank you.